Good morning, I'm Manuel Zarzo, and in this Unit 7 analysis of variance, I'm going to present 3 exercises about applications of ANOVA. This exercise number 7 is a fractional design of experiment that is called 2 power to 6 minus 3. It means that we have 6 factors at 2 levels, but it is a fractional factorial design, which means that it is not complete. The target is to determine the best conditions for improving the resistance against corrosion of metal sheets. So we have studied 6 factors, all of them at 2 levels. So the complete design would contain 64 trials, but in this case we just run 8 trials, which is a reduced number, but this is like much cheaper, obviously, than carrying out the complete design. These are the experimental values, and then we have to determine which one of these factors are relevant. And so we have to determine the optimum operative condition. Okay, so if we compute the simple effect of all the factors, so it happens that the residual degrees of freedom is just 1, so we cannot solve the ANOVA table, so this information is not reliable. But so what we have here is that the sum of squares of some of the simple effects is very small. For example, for factor B 0.1, factor E 0.1, and factor F also 0.1. Okay, so we can identify here 3 factors which are sum of squares which is very small. So what we're going to do is to group those in the sum of squares of the residual, because they are clearly not significant, and then we will get 4 degrees of freedom in the residual, which is the minimum value required. Okay, so this is what we have now: 4 degrees of freedom in the residual, which is the minimum. So now we have factors A, C, and D. Then we compute the F ratio, and then we compare with the critical value from the table. For the 3 cases, it is 1 degree of freedom in the numerator and 4 degrees of freedom in the denominator. So if we consider alpha 5%, the critical value is 7.71. And then we can see that for the 3 cases, the F ratio is higher than the critical value. So it means that we reject the null hypothesis. It means that for these 3 factors, working at a lower level or working at the higher level is significantly different. It means that the average is different at the population level. Okay, so we have these 3 simple effects which are significant. So what would be the optimum operative conditions to maximize the resistance? Well, I leave you this as an exercise, again, as in the previous video that I explained. So you have to go to the matrix, you have to go to the matrix with the data and compute the averages, and then choose the level that produces the most convenient average. Okay, and then this is another exercise number 8. This is another fractional design of experiment, 2 power to 6 minus 2, so 6 factors at 2 levels. This is an experiment that is carried out to study the effect of 6 parameters on a chemical process over the resistance obtained in one adhesive. In this case, we want to maximize this resistance. Okay, so these are the 6 factors that are tested. So the concentration of saccharose on the lower level means that we use 43 grams. The higher level means that we use 71 grams. Okay. Another variable is the amount of paraformol, the lower level 30, the higher level 42. Then the amount of NaOH, hydroxide of sodium, 6 versus 10, and then the amount of water, which is 16 versus 20, and then the maximum temperature, which is 80 degrees versus 90 degrees, and then time 25 versus 35. Okay, good. So these are this is the experimental metrics. Okay, so when we put the values -1 or 1 corresponds to these values in the experimental design. So we run out the experiment, and these are the values of resistance that we get. So the target is to maximize the resistance. So we analyze this data with StatGraphics, ANOVA, and this is what we have. In this case, it's possible to compute 15 effects, 6 simple effects which will be confounded with interactions of order higher than 2, which is good, okay? So it's very convenient that we can compute these simple effects. Also, it is very interesting that because we will be able to study 7 double interactions, because they will be confounded with interactions of order higher than 2. But as I explained in a previous video, these interactions usually are not important, are not relevant. So it means that we can assume that the effect of these interactions is very small, and then we will be able to compute those double interactions. Okay, and also 2 interactions of order higher than 2, but we are going to assume that they are not relevant. So at the end, once we have all these effects, which is like a long list, so we remove all of them which are not significant, which means that their p-value is higher than 0.05, and at the end we have that the simple effect of the first factor and the third factor is significant because the p-value is very small. It is much lower than 0.05. Okay, so we should also check that none of the double interactions are significant. You can do that as an exercise, but in this case that is true, so we don't have double interactions. And then finally the last step is to determine the optimum operative conditions to maximize the resistance. Okay, this is something that I leave you as an exercise. So you have to go to the matrix of the design of the experiment and take the values and compute the average for the lower value for the first factor, the average for the higher level of the first factor, and the same for the third factor. Okay, and then I give you the solution that you should be able to obtain. The solution is that for the first factor we should work with saccharose 43 grams, and we should use with a concentration of sodium hydroxide of 10 grams. And then, so this is the last exercise that I'm going to present in this video. This is a certain process where we measure the time. Time is a quality parameter that should be minimized. Okay, good. In this case, we study 3 factors at 2 levels, and then we study 5 factors at 3 levels. So in total, we have a lot of factors, 8. Okay, this is a fractional factorial design of Taguchi, design called L18, but we have made some kind of change. So we take the L18 orthogonal array proposed by Taguchi, but we adapt the 3rd column and the 5th column. So in here, instead of 3, we put a value 2, and here the same. Instead of 3, we put a value 2. So this is a way, an easy way to adapt this L18 table of Taguchi for this experiment where these factors are at 2 levels. Okay, well, and this is the result that we get. In this case, we just have 4 degrees of freedom in the residual, which is like the minimum. Okay, and here, if we take a look at the p-value, we can see that some of the p-values are much bigger than 5%, which means that they are not significant. We should remove them. These are also much bigger than 5%, and this also. Okay, so we should take them out and repeat the ANOVA table. And here we can see that 2 of them, the p-value is less than 0.05, and one of them is 0.13, but is more or less close to 0.05. So we repeat the ANOVA table. Now we have 12 degrees of freedom in the residual, which is much better. So it means that the information is going to be reliable. So we have that for the factor D, the p-value is very small. That for factor C, also the p-value is very small. And interestingly, here, the p-value was not significant, but here, the p-value is less than 0.05. So it means that the simple effect can be considered as statistically significant. So in order to optimize this process, we should determine the optimum conditions for factor D, G, and C. Okay, and this is to get this optimum condition, we can take a look at the LSD intervals. So for these three factors which are relevant. In this case, as we want to minimize, okay, we should choose factor C at the higher level. Okay. Again, here as we want to minimize, we should choose factor D at the highest level, and here we should choose factor G at the lower level. This is the best recommendation. Okay, the effect of G is mostly significant, okay, because the p-value is close to alpha. But anyway, so it is a good idea also to include that in the optimum operative conditions. So in case of this factor is quantitative, okay, so we can study that with multiple regression, and for sure we will get that the simple effect is clearly significant. It means that the best recommendation is to choose factor G at the lowest level. Okay, and well, extrapolation. Given the linear effect of factor G, okay, the best option is to work with the lowest level, but maybe even we can make some kind of extrapolation, and even we could go slightly lower. Okay, so this is the end of the video that I have presented about 3 exercises of ANOVA.